Hey everyone, today we're going to talk about the integral test. This is section 8.3, I believe. It's a test for convergence of a infinite series. So we're going to do lecture a little bit differently today. I have this integral test exploration that I'm going to run through with you guys, and we'll try to develop the integral test as we go. All right, so let's start out. So here, consider this sequence a sub n equals 1 over n, right? So remember, this is a sequence, so this is just a list of numbers. We're not talking about a summation quite yet. Determine if this sequence converges or diverges, okay? So just be careful here. Note that we're dealing with just this list of numbers, and we're going to determine whether that list converges, not the sum of the numbers of this list, okay? So does this sequence converge or diverge? Well, let's take a look. How can we determine whether the sequence converges? Well, we just take a limit, right? So if we take a limit as the n goes to infinity of these terms and see what we get. So the limit as n goes to infinity of 1 over n equals, well, this would be 1 divided by a really big number. That would be 0. Right? So this implies that the sequence converges to 0. So now we're going to determine whether the series converges or not. Okay, so we know that the terms in the sequence go to 0. But if we take a look at this series right here, this infinite series, called the harmonic series, okay, it's a special one. So the terms in this sequence are 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. We add them all together, we get that infinite series here, okay? So can we write this in a compact summation notation? Of course we can, right? So this is the sum as n goes from 1 to infinity of 1 over n. That's this guy here, right? Right, so now let's calculate some partial sums. So now here we're, instead of doing an infinite sum, we'll do the first partial sum, the second partial sum, the third partial sum, and so forth, right? So this is the first partial sum, so n goes from 1 to 1, so that's just the first term, that would be 1, right? Now how about the second one? So here, n is going from 1 to 2, so we're summing the terms there. Be 1 plus 1 half, just 3 halves, or 1.5, right? Third partial sum is 1 plus a half plus a third. So that would be approximately 1.833 p, exactly that. Summation 1 to 10 would be 1 plus a half plus all the way to 1/10. And instead of just plugging that in, we can actually use our calculator to get these summations. So here's how you use your calculator to perform some summation. All right, so you're going to hit second math. That's going to be the key right under alpha. So it's just hit math, not second. So just hit math. And then scroll down so you can see our nth derivative, our integral, and right below that, if you have the newer calculator in the 0 position, can't quite see that, can you? In the 0 position, you have summation, and it has the little sigma there. So if you hit that, it's going to put in a summation for you, something like that. And we're just going to fill it in. So I'm going to put my variable, we can use either n's or x's, whatever. So I'm just going to put x there. We're going from 1 to 10 and 1 over x. hit enter. So we get about 2.93 approximately. Okay. Let's do it for 100. So just change that 10 to a 100 and recalculate. Looks like 5.19 approximately. And then last, let's do it for 1,000. This might take a minute. $7.49. Okay. All right, so we can see that this guy looks like it just continues to increase, right? So we should be thinking something about the convergence of this series. So recall that for an infinite series to converge, we need, so this series here, we need the limit of the nth partial sums to be finite, which means less than infinite, right? So we know that if this limit of the nth partial sum is smaller than infinity, or less than finite, that is, then we know that the series will converge. So if we look at the pattern here, does it seem like this is leveling off? Well, it grew by 0.5, grew by 0.3 here, this grew by 1 and some change, this grew by 1 and a little bit more, then 2 and some more, so on and so forth. So you can see that there's no trend here of just kind of a leveling out after 1,000 terms, right? So if we were to do 10,000 terms, we would get some number that's larger than this. So it seems that the limit of the nth partial sums will be equal to infinity, right? It just continues to grow. Thus, sigma n goes from 1 to infinity of 1 over n diverges. Right? So we don't see a leveling off trend, so the series will diverge. So you can see that we have the sequence, the terms in the sequence are converging to 0, so they're all going to 0. However, when we add up all of those infinitely many terms, the terms don't go to 0 fast enough, which means that the series here will diverge. And you also know that this series is going to converge because this is a p series, right? This is a p series with p equal to 1, right? There's a 1 power there. We talked about p series last time. So I already know that this is a p series, a non-convergent p series, because the power is too small, okay? So let's see how this compares to the integral, and we'll develop the integral test. All right. So every series that can be depicted graphically. So here we can see the series represented by a bunch of rectangles, shaded in rectangles. Okay. So the area of these rectangles represents the series. Okay. So let's write down the sum of the areas here. So if we look at the first area, A1, A2, A3, A4, A5. What is, so the sum of all these areas would be what? Well, what's the area of this first rectangle? Well, that's 1 times 1, or 1, plus 1 times a half, which is a half, plus 1 times a third, and a fourth, and a fifth. Right? And then, of course, we'll just consider this just to keep going. So you can see this is exactly equal to the harmonic series, right? Right. So the sum of all of these infinitely many rectangles, if we continue on, is equal to the sum for the harmonic series. Okay. All right. So one of the advantages of doing this is that we can compare the area that we have to an integral, right? To an integral. So what we want to do here is carefully draw the function f of x equals 1 over x. So we're going to basically make this sequence into a function of x and then draw that curve. Okay. So let's look. When x is 1, if x were 1, we would get f of 1 equals 1. So let's put a point at 1, 1. If x is 2, we would get 1/2. Let's put a point at 1/2. 1 or 2 comma 1/2. And so on and so forth. So we go 1/3 and 1/4 and 1/5. So if we draw a curve through those points, something like that, we can see the integral, right? Or we can start to work with an integral here. So how does the harmonic series compare to the improper integral, the integral from 1 to infinity of 1 over x dx? Well, let's shade that area. So the area represented by this improper definite integral would be this area here, right? So how does the series, how do the areas of those, the sum of the areas of those rectangles compare to the improper integral? Well, we notice that all of the rectangles for the series are above that curve, right? A portion of them is above the curve. So we can see that the sum, the infinite sum, is larger than the improper integral. So here, sigma n goes from 1 to infinity of 1 over n is greater than the integral from 1 to infinity of 1 over x dx. All right? Because those rectangles lie above the shaded area. All right. Does this improper integral converge or diverge? Well, let's do it. So first we need to rewrite this in a limit form. So the integral from 1 to infinity 1 over x dx equals the limit as b goes to infinity 1 to b 1 over x dx. This integral is easy, so it's the limit as b goes to infinity, the natural log of absolute x from 1 to b, or limit as b goes to infinity, the natural log of absolute b minus the natural log of 1. We know the natural log of 1 is 0. And the limit as b goes to infinity of the natural log of b, well, you can see that the natural log curve, recall, looks like this. So as b goes to infinity, so does the y coordinate. Therefore, this is infinitely large. Okay. So we say the this diverges, right? Diverges. So this integral diverges. So what can we conclude about this series? Well, note that this value of the series is larger than the integral, and the integral is infinitely large. So that means that this series also diverges. Thus, sigma n goes from 1 to infinity whenever n diverges as well. Okay. So this is how the integral test works. We compare the series to its corresponding improper integral, and then depending on what the integral does, so will the series. Now, I would recommend that you try this one on your own. So you can pause the video here and try it out. It's just the same kind of thing. Just make sure that you graph it properly in the beginning. But I'm going to go ahead and go through with the solution to this now. Alright, so it says write down the sum that gives the area of the shaded region below. How does it compare to sigma 1 over n squared? Well, let's look. Here's A1, A2, A3, A4, A5, A6. Alright, so sum of all these areas. Again, we're assuming that this goes forever. Is the first one is 1 plus the second one looks like 1/4 plus 1/9 plus 1/16 plus 1/25 and so on. So that's exactly equal to that series, right? The area and the series are the same. Right, so now we want to carefully draw the function 1 over x squared, so let's just plug in values. At 0, well, this is undefined, so we don't have a value at 0. At 1, this will be 1, so 0.11 will be here in this corner of the rectangle. At 2, we'd be at 1/4, so 2 1/4, and then 3 1/9, and 4 1/16, and so on. So we draw this curve, something like that. All right. So if we look at that, how does the series value, which is the sum of all of these rectangles, compare to the improper integral 1 to infinity here? So if we look at the improper integral this time, it seems like we have more shaded area for the integral now, right? So sigma n goes from 1 to infinity of 1 over n squared is less than the integral this time. Now, let's determine if the improper integral converges or not. So, let's do our improper integral. So we need our limit. It's b goes to infinity, 1 to b, x squared dx. So the antiderivative of 1 over x squared. So that's x to the negative 2, increase and divide. So we'll get the limit as b goes to infinity of negative 1 over x from 1 to b. That's the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Right. So of course that's going to change to positive 1, and the limit as b goes to infinity of negative 1 over b is 0, therefore this is equal to 1. So this guy converges, right? It's finite. This integral converges. Thus, if this is a finite value, and we know that the sum is less than that, then we know that the sum also converges. Thus, sigma 1 over n squared converges. Okay. Since its value is smaller than 1. And we should have known that from the get-go, right? This is a simple series. 1 over n squared is a p-series with p greater than 1. So we know that this was going to converge by our p-series test that we did last time. Alright, so here it is. This is the integral test. So suppose that f is a continuous positive decreasing function, and let the series be represented by some function. When the series is convergent, if and only if the improper integral also converges. So if we know that the integral from 1, it doesn't necessarily have to be 1, but if we know if the improper integral converges, then we know that the series converges. And if the integral diverges, the series diverges as well. Okay. All right. So why do we think f of x needs to be decreasing? So think about what might go wrong with the geometrical argument if f of x is not decreasing. Well, it has to be decreasing, right? So if we have an increasing function on 1 to infinity, the area would be infinite, right? F of x must decrease, or the integral from 1 to infinity of f of x dx will equal infinity, right? Right, apply the integral test to the infinite series 1 over n squared plus 1 to determine convergence or divergence. Alright, so we're going to try the integral test on this guy. So let's see. A sub n equals 1 over n squared plus 1, so we want to just write this as a function of x, so just write it as a function of x, 1 over x squared plus 1. But to determine if this is decreasing, so remember, if we can determine that something is decreasing if we find that the derivative is negative, or if we do some algebraic comparison to the next term of the series. I'm just going to find the derivative because that's pretty simple. So to do so, we can use chain rule here. So f of x equals x squared plus 1 to the negative 1, and then f prime will be negative 1 x squared plus 1 squared to the negative 2 times the derivative of the inside is 2x. So that would be negative 2x over x squared plus 1 squared. And if we notice, this is less than 0 for all x greater than 1, right? Greater than or equal to 1. So derivative is all negative, therefore f of x is decreasing. We need to explain why f of x is positive here, right? Because these are conditions. Why are we doing this? These are conditions for the theorem, to the integral test to work, right? We need to have f continuous, positive, and decreasing, right? So we've just shown this. We're about to show this, and then we'll look at that as well. So continuity is pretty simple, right? Continuity is easy. There's no this is always continuous on 1 to infinity, of course, because nothing makes the denominator 0. Is it positive? Yes, since x squared plus 1 is always greater than 0, right? Right, and now our improper integral. So we're looking at the integral of 1 to infinity, 1 over x squared plus 1 dx. So the limit as b goes to infinity of the integral 1 to b, 1 over x squared plus 1 dx. So our hint says, remember there's a formula for this one, right? There's a formula that we did for this when we did the trig sub or partial fraction unit. It should be on your list of integrals. So the antiderivative of 1 over x squared plus 1 is the tan inverse of x. So this is the limit as b goes to infinity of the tangent inverse of x from 1 to b. So the limit b goes to infinity of tan inverse b minus tan inverse of 1 here. All right, so let's think about what's the tangent inverse of 1. So tan inverse means for what, this is an angle, we're looking for angles for both of these things, right? What angle is associated with a tangent value that is 1, that is pi over 4, right? Limit as b goes to infinity, tan inverse of infinity, what's that? Well, let's look at the graph of the tan inverse function. So let's graph tan inverse. Make sure your calculator is in radian mode. Clear anything out of there. So you got to do second tangent of x. Graph this guy. So what's happening with the tan inverse? Let's zoom out a little bit. So it looks like we have the tan inverse approaching some value, right? Approaching some value. So you can see the y-coordinate is increasing slightly, but ever so slightly, right? This looks like it's leveling off to a particular value. In fact, it is leveling off to a specific value, and that value is pi over 2. All right, so you see the y value is 1.532219. Quit out of that. If you type in pi over 2, see what you get. It's 1.57, right? So it's increasing towards pi over 2, but never goes above that, okay? And pi over 2 over minus pi over 4 is pi over 4. All right. So you can see we get a finite value, therefore this integral converges, and so does the series. All right, our last one. So I recommend that you do this all on your own first, and then watch the video for the solution, okay? See if you were right. So it says use the integral test to determine whether that series converges or diverges. Make sure to show how the hypotheses of the integral test are satisfied, i.e. f is continuous, positive, decreasing on, that should say 2 to infinity, because our series goes from 2 to infinity. Show all work and justification below, okay? So we need to make sure the hypotheses of the integral test are satisfied, i.e. f is continuous and positive and decreasing, okay? And then we can go through, find the improper integral, and compare it, okay? So let's do continuity. Is f continuous on 2 to infinity? Well, let's look. What values make this guy down here 0? Well, if n were 0, it would be 0. And then what the natural log of what gives us 0? If n is 1, right? So the only values that make the denominator 0 are 0 and 1. So is f continuous? Yes. N is not equal to 0 or 1. Huh? 2. Is f decreasing? Well, let's say it's f positive. Well, is n positive? Yes. Is the natural log positive for 2 to infinity? And the answer is yes. The natural log is negative for fractional values. So yes, since n is greater than 0, and natural log of n is greater than 0 on 2 to infinity. Last, we need to show that f is decreasing. Is f decreasing? Well, we can do this using a derivative or looking at the relationship between a sub n and a sub n plus 1. I like to use the derivative. It proves to be a little faster here. Okay, so let's take a look. F prime of x is equal to what? Well, we could do the quotient rule here. So the derivative of the top is 0 times the bottom minus the derivative of the bottom. We're going to have to use the product rule on, so say x here. Okay. Derivative of the bottom would be derivative of the first times the second plus the derivative of the second times the first times the top over bottom squared. So 0 times that just wipes that out. This would be negative natural log of x minus 1 over the bottom square. If we look on the interval 2 to infinity, this is positive, which means the top is always negative, and the bottom, since it's being squared, is always positive. This is less than 0. Otherwise, f prime is decreasing on 2 to infinity. So all three conditions of the integral test are met, which means that we can perform it and go through with our analysis there. All right, so we need to do our improper integral. 2 to infinity, 1 over x natural log of x dx. Rewrite in our limit form. All right, we've tackled this integral several times before. Our best method to use to integrate this is u substitution, right? If we make u equal to the natural log of x, we have our 1 over x as our derivative there. So let's say u is natural log of x, du is 1 over x dx. We also need new boundaries here. So the upper would be natural log of b, and the lower is the natural log of 2. So we have our limit as b goes to infinity, natural log of 2 to natural log of b of 1 over u du. Anti-differentiating, antiderivative of 1 over u is the natural log of absolute u. Limit as b goes to infinity of the natural log of absolute u from natural log of 2 to natural log of b. Using the fundamental theorem, we get natural log of absolute natural log of b minus natural log of the natural log of 2. Okay. So let's look. The natural log of the natural log of 2 is just some number, right? This is just some value. We can actually, if you use your calculator, this is roughly negative 0.367. All right. What about this guy? Well, if infinity goes in, the natural log of infinity, as natural log as b moves to infinity, recall, if you look at the graph of the natural log function, you just focus on this guy. The natural log as b goes to infinity is infinity, right? So this goes to infinity, and the natural log of infinity is infinity. Therefore, this is infinite minus some little number gives us infinity. Thus, sigma n goes from 2 to infinity of 1 over n, natural log of n, diverges. This diverges, say diverges as well. All right, so that does it for the integral test. I would recommend using this test when everything else fails for you. Notice that we need something that's a series that's easily integrable, right? So for a series that are easily anti-differentiated, if you think about the antiderivative, use this test. All right, you should be able to start your suggested homeworks now.